Today we are going to talk about RAID, which stands for Redundant Array of Independent or Inexpensive Disks. RAID is a technology that allows multiple physical disks to be combined into a single logical unit to improve performance and data redundancy. There are several configurations known as RAID levels, each with its own benefits and use cases. Understanding RAID is crucial for anyone looking to optimize their storage solutions, whether for personal projects or for enterprise environments. Hello everyone, my name is Sohail and welcome back to Linux and Beyond. In this video, we will learn to set up and manage RAID arrays. We will learn different levels of RAID and how each level can be used. So let's get started. Whether you are a programmer, artist, or a company who has a ton of precious data that you cannot afford to lose in case the storage disks fail, seems like RAID can fix a lot of those issues. Let's start from understanding how RAID works. RAID offers two primary benefits: improved performance and data redundancy. Both of these are achieved by spreading data across multiple disks in the array. There are several RAID levels, each designed for specific use cases. Let's understand 5 standard RAID levels, which are RAID 0, RAID 1, RAID 5, RAID 6, and RAID 10. There are many more, but these are 5 standards that we must understand. Let's start with RAID 0. RAID 0 distributes data evenly across multiple disks. It provides increased performance and capacity, but offers no redundancy. For example, consider two disks, disk A and disk B. In RAID 0, data is divided into blocks and alternately written across both disks. If you write a file of 4 blocks, the first 2 blocks might be written to disk A and the next 2 blocks might be written to disk B. This allows for faster read and write operations since the data can be accessed simultaneously from both disks. However, if one disk fails, all data in the array is lost because there is no redundancy. If you want to keep all your data accessible even if one of your disks fail in the array, you can use RAID 1. RAID 1 duplicates data across 2 or more disks to provide redundancy. It's a very basic setup. Each disk in the array contains an identical copy of the data, which offers fault tolerance and data protection. Consider two disks, disk A and disk B. In RAID 1, any data written to disk A is also simultaneously written to disk B. This ensures that if one of the disks fails, the data can still be accessed from the remaining disks. RAID 1 can save you from disaster, but there are several reasons why people may not be encouraged to use RAID 1. For example, the size of the logical disk RAID 1 provides is always equal to the smallest disk in the array. That means even if you have 100 disks in the array, each disk of 1 terabyte, the usable disk space will be 1 terabyte only. The rest of the 99 terabytes will be used to store identical copies of every file. This makes the setup much more expensive than others. If you want more usable data with redundancy, you can try RAID 5. RAID 5 distributes data and parity information across multiple disks. Parity information is used for error detection and recovery in the case of disk failure. RAID 5 provides a balance of performance, capacity, and data redundancy. Consider 3 disks, disk A, disk B, and disk C. In RAID 5, data is striped across all disks and parity information is distributed across the disk as well. For example, if you write a file of 4 blocks, the first 3 blocks might be written to disk A, disk B, and disk C, and the 4th block contains parity information. This allows for high read and write speed, performance, and fault tolerance. If one disk fails, the missing data can be reconstructed using the parity information stored on the remaining disk. Now, here's one thing to remember is that parity information is not the direct copy of files being created or stored. Instead, it's a calculated value that is used to provide redundancy and fault tolerance within the RAID array. So, because RAID 5 uses one disk to store parity information, the usable storage in the array is always one disk less than the total disk in the array. For example, if there are 100 disks in the array of 1 terabyte each, the total usable space will be 99 terabytes, which is much more than what RAID 1 provides. Now comes the RAID 6. Now RAID 6 is similar to RAID 5 but provides additional fault tolerance by using dual distributed parity. It can withstand the failure of 2 disks in the array without losing data. Consider 4 disks, disk A, disk B, disk C, and disk D. In RAID 6, data is striped across all disks and 2 sets of parity information are distributed across the disk.
This provides redundancy against the failure of up to 2 disks in the array. If you write a file of 4 blocks, the first 2 blocks might be written to disk A, disk B, and disk C, and the third and fourth block contain parity information. RAID 6 offers higher fault tolerance compared to RAID 5 but requires additional disk space for storing parity information. RAID 6 uses 2 parity disks. That is why the usable space is always 2 disks less than the total disk used in the array. If you have 4 disks in the array, each disk of 1 terabyte, the usable disk space will be 2 disks, that is 2 terabytes. Next comes the RAID 10. RAID 10 combines the feature of RAID 1, which is mirroring, and RAID 0, which is striping. It mirrors data across multiple sets of striped disks, providing both redundancy and performance. Consider 4 disks: disk A, disk B, disk C, and disk D. In RAID 10, data is mirrored across pairs of disks, and the mirrored pairs are striped. If you write a file of 4 blocks, the first 2 blocks might be written to disk A and mirrored to disk B, and the next 2 blocks might be written to disk C and mirrored to disk D. This provides redundancy against disk failures and improved performance due to striping. RAID 10 offers high performance and fault tolerance but requires a larger number of disks compared to other RAID levels. In RAID 10, the usable disk space is always half of the total disks used in the array. The other half is always used to contain mirrored data.
Selecting the appropriate RAID level involves assessing your performance, redundancy, and budget requirements. For example, RAID 0 is suited for non-critical applications needing high speed, while RAID 6 is ideal for systems where data integrity is crucial. Factors such as the number of disks available and the importance of uptimes should also be considered.
Before we go ahead and use mdadm command to create a RAID array, let's just see how many disks we have connected to our computer. So to see the number of disks connected, we can use ls command and it will provide us the number of disks connected. So as you can see, I have this device which is already being used. It stores our operating system, and these 2 devices are empty. So SDB and SDC are available to be used in the array. When we use the mdadm command to create the array, we'll also need to know the device's name that we want to use to our array. So let's see, we have, for example, we have 20 GB of disk connected to our computer, and the name is SDB, and this SDC is also 20 GB. So we want to create a disk array using these 2 disks. Now we can use mdadm command and we can pass the create option or the create command to create an array. The next one is we can provide the verbose option, which will provide us additional information in case anything goes wrong. Next, we can give the array a name. When we give RAID array name, then there's already a convention that we use, and that is we start with dev/md0. If you want to create more arrays in the future, you can just change the number and create the array. But for now, we will just create the first array, which will be typically, f/md0. The next, we need to mention the RAID level we want to use. So level equals, let's just say we want to create level 1, which is mirroring data across 2 disks. Now, the next is we also have to mention the number of these RAID devices to be used in the array. So in this case, the number of devices I'm going to use in the array are 2. And next, we can mention the name of the array. So remember what the name of the array was: SDB and dev/SDC. Now it says must be super user to perform this action. So all we have to do is type sudo, give it the password, and that's it. The array has been created. So now how do we use this array? So consider this: the device dev/md0 has been created, but it's a logical device. In order to use this, we'll have to create a file system on this device, just like we would do on physical disks. So to create the file system, all we have to do is use the mkfs command, sudo mkfs, and then the file system name, let's say xt4. I'm using the common xt4, and then the device name, so which is dev/md0. Hit enter. It may take some time depending on the size of the disk. So now, as you can see, it's writing and it has already completed. So now we have device, a logical device that has file system on it. Now we can mount this device anywhere we want, just like we would do with any other disk. Let's just create a directory inside media, and media slash RAID. The directory already exists. I probably created it yesterday. Now we can mount the logical disk on this RAID directory. Sudo mount the device that we want to mount, which is MD0, and then the directory where we want to mount this device. That's it. So now we can open up our file system and see that the device is already connected. So here's the media slash RAID. Now this is a logical device or the RAID array, and we can use it however we want. And you can also notice the size of the disk is 21 GB because I use a RAID 1 array. Now remember, in the RAID 1, the size of the RAID array is always the smallest disk in the array, which is 20 GB in this case. So now we can use this folder. We don't have permission. Now we can use the chown to gain the permission of this folder. Now we should be able to create any directory. There you go. So I can create a directory. Now whatever we store on this disk is automatically going to be stored on the other disk that we have in the array. So we don't have to worry about that. RAID takes care of that mirroring automatically. Similarly, we can create other arrays. All we have to do is change the device name or the array name, and then we can, if you want to use another level, you can use another RAID level and then change the number of devices to be used in the array and then give the device name. That's it.
So far, we have learned how to create RAID array. Now let's see how we can check the health of the array and to ensure that everything is working smoothly, and how we can add a disk in the existing array and replace a failed disk with a new disk.
When you create a RAID array and you are storing data continuously, one of the most important things is to keep your eyes on the health of the array. And to do that, we have several commands, one of which is the detail command. So we can use the mdadm command and provide the detail option, and then give it the name of the device that we want to monitor and hit enter. Now you can see all the information related to this device. As you can see, we have 2 active devices in the array, the 75 rings resync status, and these are the 2 devices being used in the array. So all this information is available here. I highly recommend you to run this command regularly. Maybe set up a cron job that runs this command and checks whether there is any error in the array. Now when you get an error, you also have something like degraded. So whenever you see degraded here, you need to immediately check for any error in the disks. If any one of the disks is not working or has failed, you will see the status of the disk will change to faulty. So then you need to immediately start the process of replacing that disk with a new disk. Now how you would start that process is not you do not immediately take out the disk and replace it with a new one. Instead, you mark that device as failed and then remove the device, connect a new disk, and then use the add command to replace the new disk in the array. Now I'll show you how we can do this. So as you can see, I have another SSD disk which is of 22 GB. Let's just say this disk has failed and is not working. So I'll safely mark this disk as failed device. And here's how we can mark any disk as failed disk. We can use mdadm command, and you can use the manage command, and then give the name of the array, which is dev/md0, and then use the fail option, and then give the name of the disk that has failed. So in this case, let's just go with stc. So now it has set the device as faulty in md0. If you check the status of the array back, then you should see that the device has been marked as faulty. So once you mark the device as faulty or the disk as faulty, then RAID will no longer use that device in the array to save data. All data will be accessed from the other device. Anyway, we can now physically remove this device. I already have the connected the other disk, which is of 22 GB, and I can replace this now using another command. Now remember, when you're replacing a disk with a failed disk with a new disk, the size of the new disk can be either equal or larger than the size of the failed device. Remember, when we created this array, we created file system on both disks. So similarly, we'll have to create a file system on SDD disk, the disk that I'm going to add to the array. So to do that, we can use the sudo mkfs command and then the xt4, which is the file system. And as always, you can use it as b3fs or xfs, whatever you prefer, and then give it the name of the device, which is SDD, and it has created. Now we can check the status back, and now I can use the sudo mdadm command, manage device, give it the array name, and then use the add command to add the disk, and it has been added. So now if you check the status, you should see something like the rebuilding is going on.
Once the replacement disk has been added and the array has finished rebuilding, it will be fully operational again, with redundancy restored. You can verify the status of the array to ensure that it is working fine and all the disks are in good conditions.
So once the rebuilding process is done, you can start using the array just like you were using before. So now you can see I have test folder and that I created before replacing the disk. If you want to remove a disk from the array, you can use the remove option like so. And now you can give it the device name. Let's say I want to remove SDD, and if I hit enter, it will start the remove process. I don't want to remove it because I have other commands that I want to show you. The other thing that we often need to do is add more disks, and that process is exactly the same as we have already followed. Connect your disk to the computer and then use the mkfs command to create the file system, and then you can use the add command like we have already used, manage, and then give it the device name, and then you can give it the device name, whatever. It will start the process. It will add the disk and rebuild the array. Now if you want to check the status of every disk connected to the array, then you can use the examine command, and the way we do this is by using the examine command and then give it the device name. Let's say I want to check the disk that I have just added, and I want to read all the metadata or that exists on this device, and there you go. So you have the version of the RAID being used, the name, the array size, and all this information is available that you may need in future for any purpose, or you want to check the status of each disk in the array, then this is how you do this. If you want to manually trigger the rebuilding process, then you can re-add any disk in the array, and that will trigger the rebuilding process. You can use the re-add command, and that will remove a disk and add it back to the array, and will start the rebuilding process.
In enterprise settings, RAID is often a part of a comprehensive data management strategy. It is used not only for performance and redundancy, but also for scaling storage solutions as the organizational needs grow. A common misconception is that RAID can replace regular backups, which is not true, because RAID provides redundancy, but it does not safeguard against data corruption or accidental deletion. For example, if you delete your data yourself, then that data will be deleted from every disk in the array, which means you will lose all your data. Therefore, it's crucial to maintain a separate backup solution. Regular monitoring and maintenance are also important for any RAID setup. Keeping firmware and drivers updated can prevent many issues. In the event of a disk failure, quickly replacing a disk and rebuilding the array is critical for maintaining the data integrity. Many organizations rely on RAID for critical operations. A notable example is the data centers, which use RAID 6 or RAID 10 to ensure high availability and data integrity. Creative professionals like myself often use RAID 0 for fast access to large video files, knowing the risk associated with the lack of redundancy. So to conclude, RAID plays a crucial role in data management strategies. It offers a balance of performance, redundancy, and scalability. Whether you are setting up a home lab, managing enterprise data, or looking performance gains in gaming or in multimedia productions, understanding RAID and selecting the appropriate level based on your needs is essential. So this is all for this video. If you liked the video, then please subscribe to the channel and hit the notification bell so you don't miss any update. See you in the next one.